Hi Year 11s and welcome to this special edition of Maths Methods. In this video we will be looking at solving simultaneous linear and quadratic equations. I apologize that I'm not there for our regular class. I hope that this video will go some way to helping you bridge the gap between reading the textbook on your own and having a teacher explain things to you during class time. So without further ado, let's launch straight in to our first example. In this first example, what we want to do is find the intersection between two graphs, a quadratic graph and a linear graph. The equations are already in the form y equals something, so we can just set the two equations equal to each other. So we can start by saying x minus 1 all squared equals 2x. And this equation will define the x values where the intersections occur. Now, in order to solve this equation, we'll need to expand the bracket and collect like terms. So taking away 2x from both sides, we get this. Now, as I'm looking at this, I'm seeing, yeah, we're not going to be able to factorize that one. So either we'll use the quadratic formula or we will complete the square. It's up to you which one you do. I personally prefer to complete the square in simple cases like this. And if I halve negative 4, I get negative 2. If I square negative 2, I get positive 4. So at the end, I get x minus 2 all squared equals positive 3. And hence, my two solutions are x equals 2 plus or minus root 3 for the points of intersection. Now that we've found the x values, what we want to do is find the y values, because I need the coordinates. Don't forget to read the question carefully. And when we find the coordinates of intersection, when we want the y values, we can substitute into either of the two equations. So now we have a choice. Do we want to substitute into the first equation with the quadratic, or the second equation, which is just multiplying by 2? And the answer is you want to use the simpler equation. So when x equals 2 plus root 3, y equals 2 times that x value, which is 4 plus root 3. Nope, 4 plus 2 root 3, because you've got to apply the distributive law. And similarly, when x equals 2 minus root 3, y equals 4 minus 2 root 3. Just skipping a step there. So the coordinates are 2 plus root 3, 4 plus 2 root 3, and 2 minus root 3, 4 minus 2 root 3. All right. Let's go to our next example. To define a tangent is actually not that easy to do. We actually don't have enough mathematics yet. We need to define something called the derivative, but we'll do that in semester 2. So for now, the way I want you to think of a tangent is a line which intersects a curve at a point and has the same steepness and direction at the point of intersection. That's my early year 11 definition for a tangent, which we will make more precise later this year. I think intuitively, you know what a tangent is. You want the line to be sort of touching at the point of intersection. These two words, steepness and direction, should remind you of the word gradient. And later in the year, what we'll want to do is define something that's like the gradient, but for curved graphs. And that's exactly what we're going to do. But that's later in the year. For now, here's what I want you to know. If you're dealing with a quadratic, a tangent line is only going to intersect the graph once. And that's actually very special. This does not happen for most graphs. If I show you another type of graph, such as a polynomial, that is no longer true. If I have other graphs, the tangent could intersect at another point. But the tangent is said to occur here rather than here. Okay? So when we speak of a tangent, we have to define a point where the tangent occurs, and that's where the steepness and direction are the same. So please note, as soon as you go away from a quadratic, it is no longer true that the tangent intersects only once. But you might get that impression because of all the practice you're going to do in this exercise. So just be aware of that. Okay, so here's our second example. The line y equals 6x plus c is a tangent to the quadratic y equals x squared. Now, if I look at the graph y equals x squared, and I draw a tangent like this with gradient 6, it should be obvious that I'm going to have a negative y-intercept. The graph's going to look something like this. We want to find that y-intercept. Find the value of c such that y equals 6x plus c is tangent to y equals x squared. And find the point of intersection. So I want this point here. What are those coordinates? Okay. Now, here's what we need to know. To do this question, we need to know that a tangent to a quadratic intersects only once. And in the previous lesson, we learned a technique involving the discriminant, which defines how many intersections there are, or how many solutions there are, I should say, to a quadratic equation. So, first we're going to say, let 6x plus c equals x squared. That's an equation that defines the x value of the point of intersection. So, here is our equation. If I only want one intersection, we're going to say let the discriminant equals 0 for one intersection. If you've forgotten, the quadratic equation ax squared plus bx plus c equals 0 has a discriminant defined by b squared minus 4ac. So in this case, the discriminant is minus 6 all squared minus 4 times 1 times negative c. Alternatively, 36 plus 4c equals 0. And if I rearrange that equation, I obtain c equals negative 9. Now, are we finished? No, because we also want the coordinates of the point of intersection. So now we need to go back and substitute c equals 9 and solve this equation. If I rearrange this equation, I get x squared. Sorry, that should be minus 9. I get x squared minus 6x plus 9 equals 0. X minus 3 all squared equals 0. You should recognize that as a perfect square. X equals 3. And if I substitute this back into this equation, which is the easier one to work with, x equals 3, y equals 9. So the coordinate of intersection is 3, 9. So just looking at this rough picture that I've drawn, that makes sense. I should have a negative y-intercept, -9, and you might not be convinced that this actually works. So that's why I've included this second part here. Let's use our calculators, our casts, to draw the graphs. I know I haven't done much work with the casts this year, and that's because I think what you did in year 10 is going to be enough for most of our work. But when we get to the end of quadratics and do applications, I plan to do more cast work there as well. So if you're feeling like, Mr. Chu, I need you to do more cast work, don't worry, it's coming. I'm aware of that. Okay, so here's a bit of cast work for you. Let's graph x squared and 6x minus 9. Now, because there are two calculators, I need to show you both. So I'm going to start with the class pad. You can actually get to the graphing window by pressing this button here, that parabola there. Now, a graphing window has turned up, but there's no way for me to type in the equations. What I need to do is press this first button here, which has y1 and y2. Now you'll see I've already got those graphs prepared, but let's suppose that I didn't and I had a brand new window. What I would need to do is type in the two equations, x squared and 6x minus 9, and then I would need to tick the two boxes to tell the calculator that I want to graph both of them. And then to draw the graph, I need to press the parabola icon again, this first one on the left here. So I press that button and the calculator draws it. Now at this point, my active window is the bottom half, and I don't really need a top window anymore. So I can get my stylus and press the resize region, and that turns it into a full window. Now when you did this, you probably won't get this. You'll probably have the default window, or what you had left over from last time, which looks something like this. If you want to change the limits of the x and y axes in your window, you need to go to the fourth button from the left with the 4 arrows pointing outwards, press this button, and then type in the values that you want. The cast can't replace your brain. You need to decide what suitable values for x and y are, and it's not always obvious. You might need to do this more than once. So what I'm seeing here is I can reduce the maximum x value, and probably the maximum y value as well. I can increase the lower y bound to, let's say, -2. And let's give it a bit more y, and we'll reduce x. Okay, so you should see, yeah, it's somewhat convincing that it's a tangent. We'll do this later in the course, but you can actually get the calculator to find the point of intersection between the two graphs. So if I go to Analysis, G-Solve, and Intersection, you'll see that that coordinate 3, 9 is actually what we found algebraically just now. Please note that if you get decimals here, it's not possible to get exact values. If you want exact values, you need to set up simultaneous equations on the CAS calculator. All right, over to the TI. In the TI, you need to go to the graphing application, which is number 2. You'll notice it's set up by default for function notation, and in Maths Methods, basically everything we draw is a function, so we don't need to change that. Our first graph is x squared, so type it in and press enter, and a graph will come up. Now, we want to type in a second graph, but the thing went away. So we need to go to Menu, Graph Entry, and Function, and you'll notice F2 comes up. That's our second graph. The graph we want to draw is 6x minus 9. Press enter, and again you'll see it's drawn the graph, but the the x and y values aren't great. So let's change that. So we'll go to Menu, Window, Window Settings, and again, you have to play with it a little bit. But I recommend maybe something like this, based on what we did on the class pad. And you can see, yeah, it does look quite convincing that this is a tangent. I'll change it on the class pad as well. I'll increase the y max to 20. And suppose I want to find the point of intersection. On the TI, I would do Menu, Analyze Graph, Intersection. And on the TI, it's a little bit different. You have to tell the calculator sort of an interval where you're looking for the intersection. So I'm seeing the intersection is somewhere between here and here. You will have to click for each boundary. Click again. And the 3,9 has come up, but it was covered by the F1 and the F2. If you want a precise point of intersection, I recommend just using the simultaneous equation solver on your CAS. But if your question just asks for decimals, you can probably get away with just doing it on the calculator in the graphing window for the intersection. Okay, so I hope it was helpful. It is very useful to be able to sketch a graph on the CAS to get a quick view of what's happening. So if you're feeling rusty from last year, I recommend practicing a little bit. Just draw a few quadratics and make sure that you can change the graphing window, because when we set a test question, we'll probably make sure that it goes off the default window. Just a top tip there, because they certainly did that in my year when I did Methods 1, 2. Because we want to know whether you know how to use the CAS. So it's perfectly reasonable that we wouldn't make the graph appear on the default window. All right, so here's our last example. This is a very challenging example, and once we complete semester 2, there'll be an easier way to do this. But I'm including this example to really stretch your understanding of tangents and of the discriminant, and to help you visualize what's happening when a parameter is involved. So here's what's happening. I've got the quadratic y equals 4x squared plus 16, and I am going to find a tangent to the graph. But I'm not going to tell you where. But when I draw that tangent, I'm going to specify a special property that the tangent goes through the origin. Question: if I define the tangent at x equals u, what value does u need to be so that the tangent goes through the origin? Now, if it's not clear what's happening, here's what's happening. So I've got a quadratic. It's not to scale. I draw a tangent, and this time, what I want to happen is that the tangent goes through the origin. And at some x value u, the tangent is specially set up so that it's through the origin. Goal: find u. Looks pretty difficult, doesn't it, right? So, what are we going to do? I don't know the equation of the tangent. I don't know the gradient, but I do know the y-intercept. So, maybe what I can do is define a tangent, y equals mx, to be the equation of the tangent. Now you'll notice I didn't write mx plus c, and that's because I know that the y-intercept is 0. So that actually simplifies our answer. You can let y equals mx plus c, and the question will still work, but you'll need to use simultaneous equations. Now, we also know that the equation mx equals 4x squared plus 16 defines the point of intersection. Now this is a quadratic equation. So 4x squared minus mx plus 16 equals 0. So what's happening here? It's a tangent. A tangent has one intersection with the graph if the graph is a quadratic. So now what I can do is say, let delta equals 0 for one point of intersection. So b squared minus 4ac equals 0. So negative m all squared minus 4 times 16 equals 0. M squared minus, now here one thing I want you to notice is 4 times 4 is 16. So I don't need to actually calculate 16 times 16. You can if you want, but m is plus or minus the square root of 16 times 16, which is just plus or minus 16. Because if I square root a positive number multiplied by itself, I just get back to that number. Now, I got two solutions. I got positive 16 and minus 16. Let's see whether this makes sense. If I go back to my picture, it should be clear that if I draw another graph, another tangent, reflected about the y-axis, I get the same thing happening. So if there's a positive u value, there's a negative u value that also works as well. So yes, there should be two solutions. Okay, so we found the gradient. Now let's see if we can find the value of u. Because I know the equation of the tangent, but I don't know where it occurs. So, here we go. I have the graphs y equals 16x and y equals 4x squared plus 16 intersecting at x equals u. So what I'm doing here is I'm saying consider the case m equals 16. Then what's going to happen is I'll have 4u squared plus 16 equals 16 times u. What I've done is I've substituted x equals u into the equations because this happens specifically at x equals u, the point of intersection. And now I get this quadratic. Or that is 4 bracket u squared minus 4u plus 4 equals 0, or 4u minus 2 all squared equals 0. Now the solution to this is u equals 2. That's for the orange tangent, the positive gradient tangent. By symmetry, if I reflect this about the x-axis, the other points where the tangent occurs is going to be negative 2. Now I don't need to repeat this calculation again. I can just say, by symmetry, other tangent occurs at u equals minus 2. I'll say when u equals minus 2. Okay, challenging example, but I hope the picture was helpful. All we needed to do was define a linear graph through the origin, allow that graph to intersect the parabola, and then set the discriminant to be 0 for 1 point of intersection. Why do we set the discriminant equal to 0? Because for quadratics, we know that there is only 1 point of intersection with a tangent. Please remember that once we move away from quadratics, which is coming soon, that's no longer going to be true. All right, so that's all from me. What I would like you to do now is have a go at the exercise. It's 3J. And if you have questions, just let me know by Teams and I'll be happy to reply to you when I can. All the best, and I look forward to seeing you back in class. Thanks, Year 11s.